The convolution integral is often very difficult for students to understand. It's a rather strange combination of two signals. In this presentation, I'll explain how we can understand the convolution integral in terms of a graphical interpretation. This is also helpful for us to understand what the convolution is when one of the functions with which we are convolving with has no analytical description. Let's start by reviewing what the convolution integral is. The convolution of x of t with g of t, denoted x of t star g of t, is the integral from minus infinity to infinity of x of tau g of t minus tau d tau. We denote this convolution as the signal c of t. The variable t in the convolution integral is a fixed time. The variable tau is a dummy variable of integration. You should think of the integral as an infinite summation. What we're doing is picking values of x at different values of tau and multiplying them by values of g at different values of t minus tau. So the integration here is being carried out with x being chosen with ever-increasing values of its independent variable tau, and g being chosen with ever-decreasing values of t minus tau. These are being multiplied together and being accumulated by the integral. To make what's happening here clear, let's illustrate with a particular x of t and g of t. So here is x of t and g of t, shown in graphical format. I now ask the question, what does x of tau look like? X of tau, plotted versus tau, looks just like x of t, plotted versus t. It makes no difference what the independent variable is called. The shape is the same. Now to find g of t minus tau, we'll perform a few operations. We'll first find g of tau. Of course, g of tau looks just like g of t. Changing the independent variable doesn't change the shape. We'll now reverse this time variable to find g of minus tau. Of course, that time reversal just flips the curve around, tau equals 0. So we found x of tau and g of minus tau. Our next step is to find g of t minus tau, and then we can actually perform the convolution integral. We'll now find g of t minus tau by taking g of minus tau and performing an advance or delay of the tau variable by t. Now the key thing here is we plotted g of minus tau versus tau. When we do an advance of t, that will shift the curve to the right on the tau axis. Now this is opposite of what we encountered before when we did an advance, which would shift the curve to the left. The reason why is because we're plotting g of minus tau versus tau. If we do a delay by t, then that will shift the curve to the left. Again, this is opposite of what you've seen before, but it occurs because we're plotting g of minus tau versus tau. And also, our delays here are by t, because we're working on the independent variable tau. This may be confusing at first, but if you study the operations carefully, you'll see that this all makes sense. The key thing to remember here is that t now shifts the curve either right or left. If t is greater than 0, the shifting is to the right, and if t is less than 0, it shifts to the left. So here we have plotted g of t minus tau and x of tau for some particular value of t. And the thing to remember is that during the convolution integral, t is a fixed value and is constant, and it is tau that is the dummy variable. So in convolution, we multiply the two functions at each and every value of tau to make a new function, which is g of t minus tau, x of tau. It's important to emphasize here that the role of t is simply to determine how far the g of t minus tau curve is shifted. Here I'm showing the product of these two functions. I have g of t minus tau, shown in red, and x of tau, shown in black. When I multiply the two functions, I'll get the function below, g of t minus tau times x of tau. You note for any values of tau where x of tau is equal to 0, the product g of t minus tau, x of tau, is equal to 0. And likewise, wherever g of t minus tau is equal to 0, when multiplied by x of tau, we get the new function g of t minus tau, x of tau, equal to 0. Now the convolution of these two signals is then the area underneath this curve, g of t minus tau, x of tau. We simply, through the integral over the independent variable tau, add up all the area that is underneath this curve. I should point out that the multiplication of the two functions in this example was particularly easy to carry out, since x of tau was a step signal. If x of tau was a more complex signal, the multiplication would be more difficult to visualize. The key aspect here is that we multiply the value of g of t minus tau by the value of x of tau at each and every tau to make a new function. Another way to think of the convolution is to think of it as the volume of a solid that is x of tau high and g of t minus tau wide. Here I am showing the same x and g signals that we saw on the previous page. Now let's look at it in a little bit more detail. You see x of tau along the vertical axis and g of t minus tau in the horizontal plane. The value of the convolution integral is equal to the volume, shown in green. Note that at those values of tau, where x of tau is 0, there is no height, and therefore no volume contributed. And where g of t minus tau is 0, there is no width, and therefore no volume contributed. This volume corresponds to the value of the convolution integral for a particular value of t, which is chosen prior to determining the volume. The value of t determines the shift of g of t minus tau. As we change the value of t, this volume will change in shape, and therefore the value of the convolution integral will change. For example, if for a particular value of t, the curves have no region in tau where they both are non-zero, then the volume will be 0, and the convolution will be 0 for that particular value of t. We refer to this as no overlap between g of t minus tau and x of tau. So we've discussed how to find the convolution for a given value of time t. What about if we look at different values of time t? How do we find the convolution in this case? So let's look at two cases for our particular g of t and x of t. In the first case, t is much less than 0, and g of t minus tau does not overlap with x of tau. So there'll be no volume, and therefore the convolution is 0. In our second case, t is much greater than 0, and we have lots of overlap between g of t minus tau and x of tau. But the thing to note in this particular case is that the tail of g of t minus tau is what's entering x of tau as it gets shifted farther and farther over to the right. Therefore, the volume is increasing slowly at this point. When g of t minus tau first begins to overlap with x of tau, we will encounter the high part of g of t minus tau, and therefore the volume will increase quickly at this point in time. When we combine together these different scenarios, we get a plot of the convolution, which looks like this. We'll now look again at convolution as the volume that is generated as g of t minus tau is slid across x of tau with increasing values of t. The following animation shows this evolution in volume with increasing t. X is shown in the vertical plane, and G is shown in the horizontal plane. For this animation, both X and G have finite duration. X is shaped like a triangle, and G is a quarter of the period of a sine wave. Let's consider a particular example. We'll convolve two functions, h of t and x of t, and these are shown in the graphs below. X of t has height 3 during the period between 0 and time t equals 5. H of t looks like a right triangle. Its height is 1 and its base is 1. The area of the triangle is 1/2. The convolution of x of t and h of t we will call y of t, and you can think of this as the output of the system, where x is the input and h is the impulse response. The first step is to find x of tau and h of tau, and of course these look just like x of t and h of t. Then we find h of minus tau, and this is the time-reversed version of h of tau. It's shown here. Now we'll slide this function, h of minus tau, over x of tau to determine the convolution. The amount of shift of the function is given by t. And for each value of t, the convolution can be found by finding the volume of the solid with height x of tau and width h of t minus tau. We'll now examine this for several values of t. We will consider 4 times, labeled t0, t1, t2, and t3. t0 is less than 0. t1 is between 0 and 1. In the case of t2, it's greater than 1 and less than 5. And t3 is greater than 5 and less than 6. These 4 cases correspond to figures A, B, C, and D shown. Case A corresponds to time t0, and t0 is less than 0. As you can see, g of t minus tau does not overlap x of tau, and therefore the convolution of g with x at time t0 is equal to 0. For case B, the value of time is t1, which is between 0 and 1. Here you can see there is some overlap between the triangle given by h of t minus tau and x of tau. The value of y for t1 is clearly positive, and it's increasing as more of the area of h of t minus tau is swept in with increasing shift. Let's now look at case C. This is for time t2, which is between 1 and 5. In this time range, the triangle of h of t minus tau fully overlaps with x of tau, and so over this range, the value of the volume is constant, and will be equal to 3, the height of x of tau, multiplied by 1/2, the area of the triangle of h of t minus tau. Because we have full overlap for t2 between 1 and 5, we can expect the output of the system to be constant over this range of time and be equal to 3/2. Our last case, case D, corresponds to a time t3 greater than 5 and less than 6. In this case, the triangle of h of t minus tau has begun to leave the overlap with x of tau. At first, a great deal of volume is lost as the high part of h of t minus tau begins to leave first. The reduction in volume then begins to slow down until time t3 equals 6, when there will be no volume at all. We know that since part of the triangle has departed from the span of x of tau, that the volume must be less than it was previously. That is, it must be less than 3/2. Therefore, the output, which is the convolution of the two signals, over this time span, must have a value of 3/2 or less and be decreasing with time. When t3 reaches a value of 6, the output will go to 0. Putting together the results from our 4 cases, we can plot the output as a function of time. This is shown in the curve at the bottom of the page, and labeled along the curve are the 4 cases, A, B, C, and D. You will note that the output is equal to 3/2 and is constant between the time 1 and 5. You will also notice that between times 0 and 1 and times 5 and 6, the shape of the curve is quadratic. The reason the shape is quadratic is because this is an integral of a linear function. This linear function is the height of the triangle h of t minus tau. I hope you see by this example that one can easily obtain the convolution of functions graphically. It also gives a lot of insight into the behavior of the system. It's important to understand the convolution operation, and you should make sure that you know how to do it graphically. I'll close this presentation by reminding you of the width property that we learned of before. It said that if we have two finite duration signals, x1 and x2, x1 being of width t1 and x2 being of width t2, that the convolution of x1 with x2 would have width t1 plus t2. Now that we've completed the graphical interpretation of convolution, this result should make perfect sense to you.